explain the idea and why it is a good solution for sorting algorithm. Yeah. Oh, Maria, join us. Good. All right. Now we have 3 students here at this point. Oh, yeah. So then, oh, I need to connect to my remote control. Yeah. All right. All right. F.1, Introduction to Quicksort. Yeah. We use the divide and conquer approach to look at this, the main idea behind the quicksort. Yeah. First, the motivation. Because at this point, we have learned several sorting algorithms. Yeah. From the beginning to this point, selection sort, bubble sort, insertion sort, merge sort, right? Yeah. So now another one, quicksort. The question, why we need to create a new sorting algorithm, right? Yeah. So from the title of the topic here, emphasize overall performance. That's the reason. We like to have a sorting algorithm with excellent overall performance. That means those sorting algorithms we have at this point, they do not have this property. They are not very good for the overall performance. First, selection sort, bubble sort, very slow. Yeah. So usually we do not use these 2 sorting algorithms. They are only for education purpose. So in the real world, we never use selection sort, bubble sort. Insertion sort, yeah, it is useful in the real world applications, but mainly for special data. When the data is almost ordered, then we can use, it's better to use selection sort. Insertion sort, yeah. So because it has that property, it can make the data that is almost sorted, get sorted very fast. That's insertion sort. The merge sort, when we need to have a sorting algorithm that can avoid poor worst case efficiency, then we use the merge sort. Avoid poor worst case efficiency. That's the reason we can use the merge sort. But now, another one, but this one, we need the best possible overall performance, the quicksort. Yeah. So let's look at the question. First, problem number 4, another time. Yeah. Here, we use the divide and conquer view on this new sorting algorithm. Yeah. So the goal, make the overall performance as fast as possible. Yeah. So this is a big goal, right? Yeah. Very big. Yeah. But to get this property, you may need to sacrifice a little bit. Okay, so this property has certain cost. You need to pay certain cost to get this great property. Yeah. So what kind of cost you need to pay? Yeah. We need to tolerate poor worst case performance. Yeah. We tolerate poor worst case performance. Yeah. It does not like it's not like the merge sort. The merge sort does not have the poor worst case performance, but this one has it. This one cannot avoid poor worst case efficiency. So we need to tolerate that. Yeah. But the good thing is the probability for the worst case is very slow. Here you may ask me, what do you mean poor worst case, right? How can you describe it precisely? Poor worst case, yeah. So if the worst case performance is like big theta of n squared, then we say it is poor. Okay, yeah. But for the merge sort can avoid poor worst case efficiency because it has n log n. Yeah. Its worst case has big theta of n log n. Yeah, so that's the reason we say it can avoid poor worst case efficiency. Yeah, but this one, so we cannot make it to have this property because we want to, our priority is the property number one, we want to have that big property. So we have to sacrifice a little bit. Okay, yeah. All right, so that's the basic requirement. Next, the view, divide conquer view. Here we do comparison with the merge sort. We use the divide conquer view on merge sort first. Then we change that view to get this new view. Yeah. Here, yeah, this chart, we can see we do comparison. Yeah. First, for the merge sort, you can see divide step is very fast. Why? Because we split the given array right in the middle. Yeah. Without any extra work, just split right in the middle. Yeah. That operation, big theta of 1. Yeah. Almost do nothing, right? Almost do nothing, right? Yeah. We just choose appropriate indexes. You know, in our programming, we just choose appropriate index numbers. Yeah, so we make the split. Yeah, left subarray, the range of the indexes. Right subarray, the range of the indexes. Then we complete the split. That's simple, right? Yeah. Conquer by recursion. Yeah. So conquer recursive function call. So we conquer, you know, the subproblems, sorting of the subproblems. Yeah. Then combine step. We need to do the merge, combine two ordered arrays, subarrays. We need to do the operation with this cost, the big theta of k. Here, k is the current data size. That's the merge sort. Okay, yeah. But when we go to this new sorting algorithm, we want to change this view. Yeah. We want to, you know, put our main effort in different places. Yeah. All right. First, so here you can see, you know, still, because the conquer step still recursion, right? So nothing special for the conquer step. Then for the divide step and the combine step, so we just you know, switch our focus. Yeah. This time we make our combine step very fast, almost do nothing. When we combine two ordered array, we join two ordered array in some easy way without much extra work. Yeah. Big theta of 1. Almost do nothing here, but at a combined step. What's that? How can you do that? Yeah. So that's in the later story, we will see that. Okay. Yeah. But here, we like to change the focus. Okay. All right. Then, because if you want to make the combined step very fast, then the divide step, you have to do a lot of work there. Yeah. It's impossible. You make your divide step a big theta of 1. The trade-off here, you can see it's a trade-off issue. The divide step, you have to do a lot of work. Yeah. So big theta of k. That's the work we need to pay in the divide step. All right? Yeah. So for the quicksort, so this time, when we divide the original array into two subarrays, we need to make arrangement carefully, yeah, with, you know, some special treatment. After that, then we can enjoy the result, the good result. Yeah. So what kind of good result? You can merge, you can combine them easily because we pay enough to make our two subarrays have very good property. All right, yeah. So here, this is the high level understanding, and after that, we need to look at the implementation detail. How can you make all these design ideas happen? Yeah, so that's the next step. All right, yeah. So let's look at the implementation part of the quicksort. Yeah. All right. How to make combined step easy? Yes, here I need to explain that question. Yeah. Big theta of 1. How can you make your combined step big theta of 1? That's just like almost to do nothing. Okay, yeah. So let's see what is the situation of that. Yeah. Almost do nothing in the combined step. We need to imagine what special property should we have for the two ordered subarrays. The first one, A subarray here, and then B subarray. Okay, yeah. Before the conquer step, they are not ordered. Okay, before the conquer step, these two subarrays are not ordered. Okay, yeah. So we have the situation, yeah. But apply the recursive function call the conquer step. Eventually, these two arrays are sorted. Okay, yeah. Now, after they are sorted, we need to merge, right? Yeah. We need to merge. But when we merge these two subarrays, we don't want to pay the cost that we pay in the merge sort. Now, in the merge sort, we merge two ordered subarrays. Yeah, although we can do that, but that cost is pretty high, right? So that cost for the merge sort, big theta of k for the merge sort, we don't want to pay this much cost. We want to have a special property to merge these two ordered arrays. We just join them together, then the whole array is automatically ordered. That's what we like to have. Okay? Yeah. Think about that. That's what we like to have. How can that happen? Yeah. Let me explain. Yeah. Because we have some freedom to put some special property in these two subarrays. We have some freedom. When you divide the original array, you have some freedom to choose how to do the division, right? So we apply that freedom. We take advantage of that freedom to get a good division on the original array. Yeah. So then when we do the merge, we just join these two subarrays and get the overall ordered array automatically. That's the picture. Yeah. How can that happen? Yeah. Let's continue the story. All right. Yeah. All right. So now we look at the join step. Yeah. When we join, under what situation, we just put them back to back. The whole array is automatically ordered. Can you imagine that picture? Yeah, we just put these two subarrays back to back. The whole array is automatically ordered. All right? Yeah. Yeah. In this way, we avoid the costly merge step that we use in the merge sort. Yeah. But it can only happen when you have some good property in your data. So we need to know that property. What is that property? We want to see it. Okay? Yeah. All right. So the goal after the conquer step, when we combine the data, we do nothing. We just put them back to back, one after another. Arrange them, A subarray, then B subarray, they're automatically ordered. That's what we want to have. Okay? Yeah. But we need to know what property we should have. So what condition do we need before conquer? Yeah. So the data on these two subarrays, A subarray, B subarray, they should have some special property. And here we need to find that property first. Okay. The property is the value of A subarray should be less than or equal to the values of B subarray. Yeah. Any value, A of I, so any value of an element in A subarray should be less than or equal to any value in B subarray. Or another view, the maximum of A subarray should be less than or equal to the minimum of B subarray. This is the desired property we want to have before the conquer step. Or in other words, in the device step, we want to make our data to have this critical property. This is the critical property. With this property, then the combined step, we just put these two summaries back to back, then they're automatically ordered, right? Yeah. Now you have the whole picture. Because this property, if you have it, you do not need to do any work in the combined step. Yeah. All right. Yeah. But the question is, how can we have this property in our device step? We know we have some freedom in our device step, but how to use that freedom to get this property? That's the biggest challenge in this sorting algorithm. Yeah, but we need to solve that problem. After we solve that problem, the whole algorithm is there. Yeah, so that's the last piece of the puzzle. Okay, this device step, last piece of the puzzle. After we overcome it, then we have the whole algorithm. Yeah. All right. The most important step, device step. Yeah. All right. The requirement. How to split the array into two subarrays, A subarray and a B subarray, such that A of I less than or equal to B of J. Yeah. So that's the current problem we need to solve. All right. Yeah. Okay. Yeah. But here, with this property, we do not require that A subarray, B subarray are sorted. No, we do not. So if you look at the A subarray, the values of the elements, usually, in general, they are not sorted. And the B subarray, they're not sorted. But the maximum of A subarray should be less than or equal to the minimum of B subarray. That's the key property we want to have. How can you get that? How can you get that? Yeah. The next step, we will see, we will find a solution. Yeah, we can get that. There is a very smart smart way, we can make it. Yeah. So let's look at the next step, F.2, partitioning in Quicksort. Yeah, that device that we call it, partitioning step, partitioning. All right. Yeah. We do partitioning. Yeah. And there is a smart way to do the partitioning to have that special property. All right. Yeah. So let's look. So this is the goal. In our partition step, this is the goal. All right. Implement the device step. All right. So let's do the analysis. Here, let's fix the implementation details. Yeah. So here, this is the original array. Yeah. We want to split it in two subarrays with this critical property. All right. Now, in our first try, we just want to make it happen That means it may not be the best way, but we just want to get it. That means we may pay extra cost. We want to get what we need, but we may pay some extra cost in our first try. Then in our second try, we want to do better. We want to eliminate that extra pay, reduce that extra pay. Okay, all right. Yeah, in our first try, let us imagine we split the original array into these two subarrays. Okay, yeah. But the question, how do we do the split? Yeah, so here, let me describe. The idea is pretty simple. Okay, yeah. In our first try, the idea is pretty simple. Yeah. Yeah. At the beginning, we do not know the sizes of these two subarrays, right? Yeah. How large is the A subarray? How large is the B subarray? At the beginning, we do not know it. Okay, yeah. But we want to get the probability the maximum of the A subarray is less than or equal to the minimum of the B subarray. Yeah, so that's the key inequality we want to have. Yeah. All right. But how do we resolve this uncertainty? Yeah. So we need some smart idea to help us get it. Smart idea. Okay. How to make it certain. Yeah. A special element to separate two subarrays. We rely on some special element in the array to help us separate these two subarrays. That special element can fix the uncertainty problem. Okay, yep, yeah. The key property of that special element is that element must be in place. That element must be in place. You know the meaning, right? In place. But it's hard. How do you know which element is in place, right? Think about it. How do you know which element is in place? It's hard to know that. Yeah. So here. So that is the, the smart idea comes in. Yeah. Yeah. We can find some special element that is in place. At the beginning, we do not know it's in place, but at the end of the device step, we know it is in place. That's the essence of this method. Okay, yeah. So let me give you that part of the story. Determine the boundary of two subarrays. That special element plays the role of the boundary of the two subarrays. Boundary, okay, yeah. That element, yeah. Here you can see the boundary element. A subarray left-hand side of this P element, then B subarray at the right-hand side of this P element, and this P element is in place. Think about that picture. That's the picture we like to have in our device step. And this P element, the reason we call it P element, because we use a special concept for this element, the pivot element. Pivot element. We want to get a pivot element to help us divide the original array into two subarrays with the desired property. All right? Yeah. So next, we need to study this pivot element. How do you choose pivot element? How do you know this pivot element is in place? Yeah, that kind of details. All right, yeah. And all the A elements in the A subarray must be less than or equal to P, and all the elements in the B subarray should be greater or equal to P. Yeah, but actually, in our implementation, we remove that equal part. Yeah, so in our implementation, we just, because otherwise, although you have the freedom, if it's equal, it's fine. You have the freedom to do that, but for the simplicity, we just make P strictly less than all the values in B subarray. Okay, all right. That's the property we like to have, but how to get it? So our next part of the story, how to get it. All right, so let's look at that part. Question: which element is used as the pivot? It looks like this element has some great property. But how do we choose an element in the given array as the pivot element? Answer is simple. Any element has an equal role in the array, right? Because we do not have any information on the values of the elements in a given array. Then that means any element has the equal chance to be the pivot. When you select pivot, you can basically make an arbitrary selection, because they have equal chance to do a good job as a pivot. Okay, there is no reason to favor one over another one. Okay, so that means you can make your random selection for the pivot element. That's simple. All right, but actually there are two parts of the steps. Two steps. The first step is simple. This one. The first step, no reason to favor any particular element. But there is a second step. All right, So based on this first property, there's no reason to favor any particular, this property, based on this one, we can make a random selection. All right, make a random selection. But there is a second half in this implementation. Position-wise, element at which position is the most convenient. Because in the first half, we make a random selection. We look at it value-wise. We look at the value. Value-wise, we do not have preference. Any element is equally good to be the pivot element. from the value wise, all right? But those elements in the array, they have different positions, right? Position wise, they have different status. Position wise, different elements, they have different status. Not equally well, okay? Not equally good, not equally good, yeah. Some elements have, yeah, so the meaning is some elements have more favorable positions than others. Position-wise, they are different. So let's look at this question. Some of the elements, they have convenient positions for the pivot element. So we want to look at that, okay? Position-wise, which position is the best for the pivot element? That question. Yeah. Here, let me use a simple diagram to answer that question. Favorable positions for the pivot. All right. Let's look at a typical position in the middle of this array. Yeah, this position. Yeah. Let's think about if we choose this element somewhere in the middle position for the pivot element. Yeah. We want to see if it is convenient or not, if we use it as the pivot. Yeah. First, we know, in general, this element is not in place, right? Yeah. You pick some element in the middle. How do you know it's in place? You do not know it is in place. Okay, so that means at the end, if you want to put it in place, you need to move it, right? You need to move it to a different location, position, to make it in place first. Yeah. Second, when you move elements in A subarray, B subarray, when you use this one as the separator for your A subarray, B subarray, this element is like a roadblock. Okay? For example, when you want to move elements from its left-hand side to its right-hand side, or from its right-hand side to its left-hand side, this one, this position is like a roadblock. You need to do a lot of work to overcome this roadblock, right? Yeah, that's not convenient. Okay, every time you need to do some extra work to overcome this roadblock, it's not convenient. Can you find some special positions in the array that won't be a roadblock? And some special positions in the array, you will not have the situation like this roadblock one. You do not need to do any extra work to overcome the roadblock. Okay. All right, yeah, that is, yeah, you can find those special positions. The first element in the array or the last element in the array. These two positions very special because they are at the end of the array. And when you move other elements around, when you make adjustment on other elements, you do not need to touch the first element or the last element because they are not, they never block other elements, right? Think about that. These two elements, they never block other elements. Okay? Because they are not in the middle when you move other elements, right? They are at the end positions. So that's the great thing we like to take advantage of. Okay? That means we should use one of these two positions for our pivot element. One of the two positions. Leftmost position or rightmost position. They are equally good. Equally good. Okay. Some implementation uses the leftmost position, and some of the implement use the rightmost position. Okay. Yeah. Yeah. Just as the personal preference. All right. But in our algorithm here, I may choose the rightmost position. Yeah. Our textbook, choose the leftmost position. Yeah. All right. Yeah. Yeah. So here, let's look at this picture. So we pick our rightmost element as the pivot element. And then we do the split. Yeah. When we do the split, after the divide step, we want to get the left part of the array to be the A subarray and right part of the array as the B subarray. Okay, yeah. We need to move the elements around. To make this happen, we need to move some of the elements. Yeah. But the destination is like this. Yeah. And the property A of I less than or equal to P and P less than, actually less than B of J. Okay, yeah. At the end, we want to have this. Okay, all right. F.3 implementation in partitioning. Yeah. Now, we need to fix that detailed part. The last part of the detail. Yeah. All right. Straightforward implementation. Straightforward implementation. Yeah. In our first try, straightforward implementation, we use auxiliary arrays. Auxiliary arrays. Yeah. We want to make the implementation as easy as possible, but the auxiliary array we treat as the extra resource. This is extra resource to use. Okay, yeah. All right. With this extra resource, then the split is very simple, very straightforward. Yeah. All right. So we just scan the array from left to right. Okay. All right. So then when you get an element that is less than, because you choose the last element as the pivot, then you scan the element from left to right on the original array. When you get an element, if it has the property, its value less than or equal to P, you place it in the A subarray. When you see an element that is greater than P, you put it in the right subarray. How simple it is. Yeah. One scan from left to right, you will make it. You will get the split, A subarray and B subarray. After that, you just copy your data back to subarray, you copy back to the original array. Okay? Yeah. That's the split. So we get what we need. Yeah. But here, there is the problem. You use extra resource. Your method can be improved because the extra resource you use could slow down your overall algorithm. Slow down. We want to avoid that. We want to eliminate the extra resource that we use in our first try. So in our second try, we want to eliminate that extra resource. So we do not copy data from two auxiliary arrays. We do not use two auxiliary arrays. We just move the elements within the original array. Within original array, yeah. We move elements around. Yeah. That's the reason, because when we choose the favorable position for the pivot element, we consider that issue the roadblock, right? Yeah. We do not consider the roadblock positions. So we already consider moving elements around. And here we need to do that. Moving elements around within the original array. Yeah. Here, let me, yeah. So, and this first try, this solution is not acceptable because it uses too much extra space. The extra space it uses the same as the original array. Same amount of space as the original array. That cost is too high. That cost is too high. So we don't like to do that. Yeah. All right. We can use extra space, but the extra space should be limited to some small number of extra space. Okay, yeah. So here, there is a concept I mentioned before, yeah, because it's a long time ago. So probably many of you already forget that concept. So that concept is called, there is a special algorithm called in-place algorithm. In-place algorithms. And here, this in-place is different from our usual meaning of in-place. The elements are in place, that meaning. Here, not the elements in place. Here, the algorithm in place. What do you mean algorithm in place? Its meaning is the extra space used. Because when we run the algorithm, we need to use certain extra space. The extra space used is big theta of 1. That means the in-place algorithms. Here, our first try, it's not in place, right? Because the extra space used big theta of m. So it's not in place. This algorithm is not in place. So we want to get an in place algorithm. We want to improve it to make it in place. This algorithm in place. That means we want to make the extra space big theta of 1 here. Then it is much better. We use the minimum extra space so we can make it very fast. All right. So the next thing we need to do, make it in place. All right. Yeah. All right. Here we want to eliminate the auxiliary to arrays. Yeah. right? Yeah, okay. Control extra space used. Now, so we carefully control extra space used in a stingy way. Yeah, we do not want to waste unnecessary space here. Okay, yeah. All right, so how to get that? Here, let me describe the basic idea here. And then in our next part, I will show you a concrete example to see how to make it. Yeah. All right. Because we need to do elements manipulation within the original array. So we control all the positions in our original array into several different regions. First, we define some S region. S here means smaller than P, okay? Smaller or equal to the elements in this region should be smaller or equal to P. Yeah, let's call S region, right? Then L region, the elements in this region should be larger than P. So that's the L region, all right? Then the U region, the elements in this region are unprocessed. Because we haven't processed those elements. Yeah. So U region. So we divide our original array into these three regions, and we control these three regions. The purpose is to save extra space used when we move elements around. All right, yeah. So how to control in A subarray? Yeah, we put the elements in A subarray in S region. Yeah, and initially it is empty, right? At the beginning, we do not know any element in the A subarray, so it is empty. And in B subarray, we'll put it in L region, and at the beginning, it's also empty. Yeah, these two regions initially empty. Okay, yeah. Later, when we do processing, we grow these two regions. When we add elements into these two regions, we grow these two regions. All right, and for the unprocessed region, U region, at the beginning, it's the whole array except the pivot element. Yeah, excluding the pivot element. It's the whole, all right? And then we shrink this U region. We shrink, yeah. When we process element by element from this U region, it is shrinking, yeah. And the other two regions growing, yeah. And eventually this U region is empty. That means we complete processing of all the elements, and we will have the final S region and L region. Yes. Then we complete the partition step. Okay? Yeah. So that's the basic idea. Yeah. All right. So next part, I like to use one concrete example to show you how to do it, how to do partitioning in using diagram. So you can see better. Okay, so let me run that animation, that diagram. Yeah, so you will see step-by-step details here. All right, the given array, 7 elements. Yeah, the given array is like this. Yeah, and we choose the last element as the pivot element. Then we scan the elements other than the pivot from left to right and use 3 regions to control the status of all these elements. Yeah. The 3 regions, I use 3 different colors. U region, I use white color. Yeah. These, initially, all these elements are unprocessed. Yeah. So they are all in white color. Yeah. All right. So, but I need an extra space to do the swap operation. In order to move elements around, I need an extra space for the swap operation. That's enough. Okay, 1 extra space for the swap operation, that's enough, because that would give us big theta of 1 in place algorithm. The step is in place, at least. All right, this step is in place. Yeah, for the whole algorithm, that's another issue. Yeah. But just this step is in place. All right. Yeah. All right. Now let me run the animation here. All right. When we start, our S region, L region, both empty like this. Okay. Step 1, let us compare the first element 2 with the pivot element 4. And we know it is less than pivot, so it should be in S region. So we place it in S region and we grow S region. And we make the S region yellow color. So you can see we have the S region in yellow color. The second element, 8, we compare 8 with 4. It is greater than 4. So we should put it in L region. And here I use the green color. Yeah. So now we also grow the L region. Next element, 7. Yeah. It's greater than 4. So we should put it in the L region. And then we grow L region. Okay, yeah. Next one, we compare 1 and 4. It's less than 4, so we should put it in S region. Yeah, so here we make that 1 in yellow color, but you can see from the picture, you can see the yellow region is separated by that green region. That's not convenient. We want to make all the elements in the yellow region adjacent each other. They're not separated. Yeah. That means we should make some adjustment to make all elements in S region in one cluster, yeah, not scattered in different places. So that's not convenient. Yeah. So to do that, think about what is the easiest way to make 1 and 2 adjacent in that S region. Yeah. The solution is very simple. Think about the solution is if we do 1 swap operation between 1 and 8. Yeah, we just swap 8 and 1. Here we can use the extra space to do that swap operation. After the swap, then you can see all the elements in S region are adjacent each other. are in one cluster, yeah, and the L region, all the elements in L region, they have the same property, then it is very convenient. Okay, yeah, just one swap operation, we can fix it. Yeah. All right, yeah. Next step, compare 3 with 4. It is less than 4. That means it should be in S region, and we need another swap operation. Swap 7 and 3. All right, yeah. After the swap operation, then our S region, L region are pretty good, in good position. All right, yeah. Then the last element, 5, the 5 is greater than 4, yeah, so it is in L region, but we need to do the last step. We need to put the pivot element in place, the last step, in place, another swap, 8 and 4, the last swap operation. After that swap operation, 8 and 4, that's the desired situation we like to have. The pivot element is in place. Okay? Then it's the left subarray, all the elements in left subarray less than or equal to 4, and all the elements in the right subarray are greater than 4. Okay? Yeah. With this property, the combined step is trivial, right? Yeah. Automatically, the combined step. We do not need to do anything special. The combined step is there. Yeah. And we only need to use the recursion to do the conquer step. Yeah. And every time when you need to do the divide step, you apply this partitioning step. Yeah. So this is the partitioning step, a typical partitioning step. Okay, yeah. So from this example, yeah, so you can see all the details of the partitioning step. All right, yeah. Yeah. So then you have the whole picture, the whole story of the quicksort. So this is the quicksort. Okay, yeah. So if you write a code to implement all these details, then you get a quicksort. Okay. And in this quicksort, you can see it cannot avoid the worst case, right? It cannot avoid the worst case. Yeah. Here, let's look at the worst case first. Yeah. Because the question is, how do you know the pivot element is right in the middle? Yeah. Here in this example, I choose the pivot element. In my example, I intentionally make the pivot element right in the middle, but in the general case, no matter how do you choose your pivot element, you cannot guarantee it is near the middle. Yeah. You may select the pivot element at the left end or the right end, right? It's possible. The pivot element happens to be the leftmost element or the rightmost element. That could happen if the pivot element is at the end positions, 2 end positions, then you get a worst case. Because your split is extremely unbalanced. where the device step results in an unbalanced partition, then your performance is slower. All right, if all the partition steps result in extremely unbalanced cases, then you get the worst case. That's the worst case. All right. So all right. Another question: how to control S region and L region? Another technical. So this is the technical question. When we do programming, we need to fix this detail. Control S region and L region. It's pretty easy. Control S region, L region, we just use, index variables. 2 index variables, we can control these 2 regions. I index variable and the J index variable, so we can control these 2 regions. For S region, it occupies the positions of the original array from 0 through I. L region occupies the position from I plus 1 through J. Then we just change the values of I and J carefully to control these 2 regions. Okay? All right. So change I and J. What do S region, L region stand for? S region stand for the elements in this region smaller or equal to pivot P. Smaller. S represents smaller. Okay? Smaller or equal. Equal we also include it. L region larger, right? Larger. I mean, just tell us the elements in this region should be larger than P. All right. You unprocessed. You understand. Unprocessed. If you because we haven't do any comparison. The elements in the U region, we haven't done comparisons with the pivot element. All right. Okay. To change I and J, when we grow S region and L region, we swap 2 elements. All right. Here. So when we swap, I plus, right? So we grow S region. Grow L region J plus, right? So you can see it's very easy to control. But we need to do appropriate swap operations. Okay? All right. So that's the implementation details. I have 2 topics left. I leave to the next time. That's for the best case and the worst case discussion for the Quicksort. So then we will complete the whole module divide and conquer approach. Okay. All right. So let's stop right here.